So now let us take the next topic, and that is equivalence classes or partitions. Now in this, let us take the same example that we have discussed just before to understand what is an equivalence class, what is a partition and all. Now in this example which we have just discussed before, and we have proved that R is an equivalence relation. Here we are mapping the relation R from set Z to set Z, correct? So let us take two sets, set of integers and set of integers. Now the mapping will be done under this relation R only if A minus B is divisible by 2. When is A minus B divisible by 2? When A minus B is even number. When is difference of two integers even? Only when either both are even or both are odd. Let us take an example. Here, let us move this diagram little away. Now let us take an example. Let us take difference of two even numbers, and it is an even number. Difference of two odd numbers, that is also an even number. If you are taking difference of even minus odd or odd minus even, you are getting an odd number, right? Not only in this example, it is true for any general two even numbers and two odd numbers. You can see that as well. If you take 2k1 minus 2k2, this can be written as 2 into k1 minus k2. So therefore, we got even minus even is equal to 2 into k1 minus k2. k1 minus k2 is an integer. So therefore, 2 into integer means we got difference of two even numbers as an even number, right? In the same way, let us take two odd numbers. 2k1 plus 1, which is an odd number, minus 2k2 plus 1. So here 1 is getting cancelled. And we have 2 into k1 minus k2. So therefore, again we are getting an even number. So what did we understand now? We understood that difference of two even numbers will be an even number. Difference of two odd numbers will be an odd number, will be an even number, right? So therefore, let us use the same thing here. Let us get back the mapping diagram. If I am taking minus 2, because minus 2 is an even number, right? Minus 2 can be written as 2 into some integer. So minus 2 is an even number. If I choose minus 2, I can map only with even numbers on the right hand side. Only then the difference will be even, right? So minus 2 can be mapped to minus 2, minus 2 can be mapped to 0, minus 2 can be mapped to 2, minus 2 can be mapped to all even integers on the right hand side, even integer set. In the same way, if we take an odd number from the left hand side, let us say minus 1. Because minus 1 is an odd number, we can map with all odd numbers on the right hand side, right? Okay, so any even integer from the left hand side can be mapped with all even integers on the right hand side. Any odd integer on the left hand side can be mapped with all odd integers on the right hand side. Clear? Fine. So now let us move this diagram. Let us write the same information in a simple manner. Let us take two sets, set Z, set Z. Our relation R is there. Now let us represent E for all even numbers in integers. And let us take O for all odd integers in integers. So we have E and O on the left side integer set and E and O on the right side integer set as well. Now what is happening here? Just before we have discussed, every even integer is mapped to all even integers. Means every even integer is mapped to all even integers. Means E to E, there is a mapping from even integers to even integers. Correct? All even integers are mapped to all even integers. Isn't it? Let us take back that diagram once. If you take 0, 0 is mapped to all even integers. If you take 2, 2 is mapped to all even integers. In the same way, all other even integers. So therefore, any even integer is mapped to all even integers, right? So therefore, E to E mapping is happening. And O to O mapping is also happening. Any odd integer is mapped to all odd integers. So if you are taking any even integer here, any even integer, it is mapped to all even integers here. Any odd integer, all odd integers. So even to even mapping is happening, odd to odd mapping is happening. clearly you can see that set Z, which is our first set, and also you can take the second set, both the sets are divided into two partitions, even set, odd set, right? Even to even mapping is there, odd to odd mapping is there. So therefore, this relation R has divided the set of integers into two different partitions. Even integers, one partition, odd integers, other partition. Clear? Fine. So the number of partitions here is 2 because R has divided the set Z into two partitions. What is the first partition? You can say even number set. What is the second partition? You can say odd number set, right? So that is what we have to understand. This is not just true in this relation. It is true in any equivalence relation. In any equivalence relation, the relation will divide the set under consideration into partitions like this. Maybe it is not two partitions. Maybe it is more than two partitions. Okay, that depends on that relation. So on the whole, what did we understand? You take any equivalence relation, the mapping will be in such a way that the set will be divided into partitions and each partition is mapped onto the same partition. Here, E is mapped onto E. O is mapped onto O. Let us say there was third partition, P3. P3 is third partition. P3 will be mapped to P3, like that. Okay, fine. So here let us take a small example where we have 5 partitions. So what will happen? P1 will be mapped to P1. P2 will be mapped to P2. P3 will be mapped to P3 and so on like this, right? So now you have understood how a equivalence relation divides the given set into partitions. All that will be asked in the exam is into how many partitions this relation divides the given set. And for that, you have to just make this mapping diagram and see how many partitions are coming. Okay, so now let us take some properties that we have studied just now. Let us write them down. So the properties are what we have studied just now, that all elements of an equivalence class are related to each other. This partition has another name also. It is called equivalence class. Okay, so before you have seen E is mapped to E. So every element of this partition is mapped to every element of this partition, right? So therefore, every element of a partition or equivalence class is mapped to every element of the same partition or equivalence class. That is what we are writing here. The next one is no two equivalence classes have an element in common. You have seen just before, even number set, odd number set. Is there any intersection? No. So that is true in every partition. Let us say you have 5 partitions as we have discussed just before, right? In that diagram. P1 intersection P2 will be null set. P2 intersection P3 will be null set. Likewise, you take any 2 partitions, the intersection will be null set. That is what we are writing here. So there is no mixing here. Clear division. That is why you call partition. So partition 1, partition 2, partition 3, partition 4, partition 5, like that. Okay. So the last one is if you are taking the union of all of these partitions, you will get back the set under consideration. Before it was partition means even number partition and odd number partition. If you are taking the union of these 2 partitions, you are getting set of integers. In the same way, we have taken 5 partitions. Again, the same thing. If you are taking P1 union, P2 union, P3 union, P4 union, P5, you will get the set under consideration. Got it? So that is what is equivalence classes or partitions. These are the only points you have to remember. When you have a question, just see how the mapping is happening. This is an equivalence relation. So therefore, means when you draw the set diagram itself, you will be able to see. We will do one question at the end of this video and you will be very clear how to attempt problems like this. Okay? Hello students. Now let us discuss the number of relations that can be defined from set A to set B. The number of elements in a set is called cardinal number of a set. So let's say the number of elements in set A is M and number of elements in set B is N. So therefore, cardinal number of set A is equal to m and cardinal number of set B is equal to n. Relation is a subset of Cartesian product set. So if we want to find the number of relations, then we should know the number of elements in A cross B. To find that, let us take set A and set B. Let us take some elements in set A and set B. Let's say the elements are A1, A2, A3, so on up till Am. And let's say the elements in set B are B1, B2, B3, so on up till Bn. Now, what is A cross B? A cross B is every way of mapping from set A to set B. All those ordered pairs, if you are putting in one single set, then that is A cross B. So therefore, because of A1, we will have n ordered pairs. Because of A2, we will have n ordered pairs. Because of A3, we will have n ordered pairs. Because of Am, we will have n ordered pairs. So therefore, here we have written all of this sum. So how many times are we getting n? We are getting n m times. So therefore, this sum is equal to m into n. So the same thing can be written like this also, n of A into n of B. So therefore, number of elements in A cross B set is equal to n of A into n of B. So if you want to find the number of elements in A cross B set, then just take the product of number of elements in each of these sets. So here it is n of A into n of B. Okay? As relation is a subset of Cartesian product set. So therefore, choosing zero ordered pairs from mn ordered pairs can be done in MNC zero ways. In the same way, choosing one ordered pair from mn ordered pairs can be done in MNC one ways. Choosing two ordered pairs from mn ordered pairs can be done in MNC two ways. And similarly, choosing mn ordered pairs from mn ordered pairs can be done in MNC mn ways. Now, taking the sum of all of these quantities is nothing but the number of relations that can be defined from A to B, isn't it? So, how do we find this sum? Let us see that. By seeing this sum, we should remember something that we have studied in binomial theorem chapter. In binomial theorem chapter, we have studied the expansion of 1 plus x whole power n, and that is equal to nc0 plus nc1x plus nc2x square, so on like this, ncn x power n. The only difference between this sum and this sum is n should be replaced with mn and x should be replaced with 1. By doing which, here we have the required sum and here we have 2 power m into n. So therefore, the number of relations that can be defined from A to B is equal to 2 power m into n. The same thing can be written as 2 power n of A into n of B. What is n of A into n of B? That is nothing but n of A cross B. So therefore, the same thing can be written as 2 power n of A cross B. So therefore, if we have number of elements in set A as 5, number of elements in set B as 10, then the total number of relations that can be defined from A to B will be 2 power 5 into 10, which is 2 power 50. Let's say our relation is defined on A. So therefore, our relation is a subset of A cross A. So then our formula will be 2 power n of A into n of A. So that will be 2 power n of A square. So if our n of A or number of elements in set A is n, then our formula will be 2 power n square. So if n of A is equal to 5, let us say. then the number of relations that can be defined on A is equal to 2 power 5 square, and that is 2 power 25. Okay, so now let us take some CET questions. The first question is the binary relation 1, 1, 2, 1, 2, 2 and so on the set 1, 2, 3 is, we should say if it is reflexive, symmetric, transitive or not. Okay, so how do we check it? The given set is, let us say A, 1, 2 and 3, and the given relation R is 1, 1, 2, 2. Acha, 2, 1 is also there, and next 2, 3, 2, 4, 3, 1 and 3, 2. Okay, fine. So is it reflexive or not? For checking reflexive, 1, 1 should be there, 2, 2 should be there, 3, 3 should be there. 3, 3 is not there, so therefore it is not reflexive. And next is it symmetric? Let us go ordered pair by ordered pair. 1, 1 is there, flip 1, 1 is also there. 2, 2 is there, flip 2, 2 is also there. 2, 1 is there, 1, 2 is not there. So therefore it is not symmetric. Is it transitive? Yes, let us check. 1, 1 is there, and any other ordered pair starting with 1? No. So checking is not needed on this. Next, 2, 2 is there. Any other ordered pair starting with 2? Yes. So 2, 1 is there. 2, 3 is there. 2, 4 is there. Okay, so checking is completed. 2, 1 is there, and any other ordered pair starting with 1? Yes. So 2, 1 is there. That's it. So 2, 3 is there, and here 3, 1 is there. So 2, 1 is there. Next, 2, 3, 3, 2. 2, 2 is also there. 2, 4, and no other ordered pair is starting with 4. So no checking is needed. 3, 1 is there. Any other ordered pair is starting with 1? 1, 1. So 3, 1 is present. Okay. Next, 3, 2. Any other ordered pair starting with 2? Yes. So 3, 2 is present. 3, 1 is present. 3, 3 is not present. So clearly we can see 3, 1 is there. Sorry, 3, 2 is there. 2, 3 is there. But 3, 3 is not there. So therefore this is not transitive. This you can say is method 1. You know, we have done the normal way, general way. But if you are doing in CET question, CET, then you can do it like this. It is very simple. See, for checking reflexive, 1, 1, 2, 2, 3, 3 should be there. Is 3, 3 there? No. So therefore, it is not reflexive. That is clear. So therefore, this cannot be the answer. This also cannot be the answer. Next, 2, 1 is there. Like you can go one by one. So 1, 1 is there. Flip of 1, 1. That is 1, 1 is also there. We are checking for symmetric. 2, 1 is there. 1, 2 is not there. So therefore, it is not reflexive. It is not symmetric. So not reflexive, not symmetric will be only option C, right? So therefore, you see, you don't need to check for transitive. The answer is already there. Simple, right? So let us take the next question. Given set A is equal to 1, 2, 3, the relation R is 1, 2, 2, 1 and 2, 2. The relation R will be reflexive if 1, 1 is added and so on like that. So let us take the set which is given 1, 2 and 2, 1, 2, 2. Okay. And the given set A is 1, 2 and 3. Okay. Will it be reflexive if we add 1, 1? Let us see. If you are adding 1, 1, then 1, 1 will be there. The extra, I will write it here. Okay, this is an extra which we are adding. So 1, 1 and 2, 2 is there. 3, 3 is not there. So it will not be reflexive if 1, 1 is added because 3, 3 is not there. Next, will it be symmetric by adding 2, 3? Let us check. 1, 2 is there. So now we are adding 2, 3. So 1, 2 is there. Flip version 2, 1 is there. So put a tick mark on both of them. Next, 2, 2 is there. Flip of it. That is 2, 2. That is also there. 2, 3 is there. Flip of it. 3, 2 is not there. So therefore, this will not be symmetric by adding 2, 3. Next, will it be transitive by adding 1, 1? Let us see. So now we are adding 1, 1. So 1, 2 is there. Is there any other ordered pair starting with 2? Yes. So 1, 1 should be present. Okay. 1, 2 is there. 2, 2 is there. 1, 2 should be present. So therefore, checking on this for transitive is completed. Next, 2, 1 is there. Any other ordered pair starting with 1? Yes. So 2, 2 should be there. Yes, it is there. Next, 2, 1 is there. 1, 1 is there. So 2, 1 should be present. Yes. So therefore, put a tick mark on this. Next, 2, 2 is there. Any other ordered pair starting with 2? Yes. 2, 1 should be there. It is there. Okay. Next, so there is no other ordered pair starting with 2. So put a tick mark here. 1, 1 is there. Any other ordered pair starting with 1? Only this one. So 1, 2 should be present, which is present. So therefore, all tick marks. So therefore, this is transitive if 1, 1 is added. Okay. Now this is the normal general method. The quick method is, okay, so here we have a relation 1, 2, 2, 1, 2, 2. So already this is symmetric, right? Already this is symmetric. 1, 2 is there, 2, 1 is there. So put a tick mark. Next 2, 2 is there. Flip of that 2, 2 is also there. So put a tick mark. So therefore it is symmetric. Now by adding 2, 3, we are disturbing the symmetric, right? It is already symmetric relation. Now we are disturbing it. So certainly this and this will not be the answer. Correct? Next is reflexive if 1, 1 is added. Just by adding 1, 1, it will not be reflexive because 3, 3 is missing. So the correct option will be C. Okay, fine. Let us take the next question. Let Z be the set of integers and R be a relation defined in Z such that A, R, B if A minus B is divisible by 5. Then R partitions the set Z into dash pairwise disjoint subsets. So clearly we can see here the word partitions is there. So this question is coming from equivalence classes or partitions. So we have to find this R is dividing this set Z into how many partitions. We have done a similar example in equivalence classes where we have taken the example as A minus B is divisible by 2. Here we have 5. There the answer was number of partitions was 2. Here the number of partitions, you can guess it, that will be 5. But why are we getting 5? Let us understand that. If you are taking an integer and if you are dividing, let us say, by 2, then the possible reminders are 0 or 1. It will be 0 if the integer is even, and the remainder will be 1 if the integer is odd. So what I am saying is any integer can be written as 2k or 2k plus 1. And we got the number of partitions as 2 because even was being mapped to even and odd was being mapped to odd. So any 2k type number, if it is mapped to any 2k type number, then the difference will be divisible by 2. And any 2k plus 1 type number, if it is mapped to any 2k plus 1 type number, then the difference will be divisible by 2. Why? Something like this. 2k means 2 into some integer and 2 into some integer. So here I have taken 2k1 some element and 2k2 another element. So if you are taking the difference 2 into k1 minus k2, difference of two integers is an integer because k1 is integer, k2 is also integer. Integer minus integer is integer. 2 times integer, which is an even. So therefore even number will be divisible by 2. Similarly here, you will have 2k plus 1 minus 2k2 minus 1, right? So therefore plus 1 is there here and plus 1 is there here. So ultimately 1 will get cancelled. Again you will get the same thing. So therefore again you are getting an even number and even number is divisible by 2, right? So the same thing with 5 also, or with any integer also. Let us do with 5. Remainder will be 0 or 1 or 2 or 3 or 4. These are the only possible remainders. So therefore, any integer can be written as 5k or 5k plus 1 or 5k plus 2 or 5k plus 3 or 5k plus 4. Okay, fine. These are 5k type numbers, means 0, 5, 10, minus 5, minus 10, so on like that. 5k plus 1 means on dividing that integer with 5, you should get remainder 1, like 6, 11, 16, minus 6, so on like that. And so on and so forth. So basically what are we understanding here? So integers are either 5k type or 5k plus 1 type, 5k plus 2 type, 5k plus 3 type, 5k plus 4 type. Only 5 types are there. Okay, any integer you take, it will fall into any of this type. And the same thing we can do here also. If you are taking two sets, and this is set Z and this is set Z, and we are seeing how the mapping is under this relation R. So here we have 5k type numbers, 5k plus 1 type numbers, and so on like this, 5k plus 4 type numbers. Again here also the same thing. So like here, if I am mapping 2k to 2k type number, here, if I am mapping 5k to 5k type number, then same thing, 5k1 minus 5k2. So 5 into k1 minus k2. K1 is integer, k2 is integer. Integer minus integer is integer. So 5 into integer will be divisible by 5. So when I map 5k type number to 5k type number, the difference will be divisible by 2. The difference will be divisible by 5. And the same thing here also. 1 will get cancelled, again divisible by 5. So that is what we are getting here. So therefore, how many number of partitions is this Z divided into? 5 partitions. So therefore, the answer is 5. Okay, let us take the next question. Define a relation R on A is equal to 1, 2, 3, 4 as X, R, Y if and only if X divides Y. Means the first coordinate should divide the second coordinate. Then R is, okay, so we have to see if it is reflexive, symmetric or transitive or not. So to do that, now we can write the whole relation. That is not at all difficult because we know very well how to write, what is the rule and all of that. But let us not write everything. We have an easier way of doing it. Let us do it. Now, for it to be reflexive, what ordered pairs should be there in this relation? 1, 1 should be there, 2, 2 should be there, and so on like that. 4, 4 should be there. Every number is divisible by itself. So therefore, this one will be divisible by this one, right? That is what we should do. X divides Y. So this 2 will divide this 2 and so on like that. Every number will divide itself. So therefore, this is reflexive. Okay, checking for reflexive is completed. Will it be symmetric? Okay. Now let us take some example. 1, 2 will be there because 1 divides 2, right? 2, 1, will it be there? No, because 2 does not divide 1, right? 2 does not divide 1. 1 divides 2. So therefore, this does not belong to our relation. So therefore, this will not be symmetric. Will it be transitive? Okay. So actually, if you see the options, you can eliminate the options and come to the answer. Is it symmetric? This is not symmetric, we found out. If a relation is not symmetric, it is not. Equivalence, it is not symmetric, it is not symmetric. So therefore, answer is option A. And you can check for transitive. You can write the whole relation and you can check it, but already we got the answer, right? So there is no need to check for transitive. Okay, so let us take the next question. Let S be the set of all real numbers, okay? And a relation R has been defined on S as A R B implies and implied by mod of A minus B is less than or equal to 1. So we are mapping from real number set to real number set, and A will be related to B if the condition is the difference magnitude should be less than or equal to 1. Will it be reflexive? If A, A belongs to R, then it will be reflexive. That means both are A. That means 0, mod 0 is 0. 0 is less than or equal to 1 is true. So therefore, it will be reflexive. Okay. Next, will it be symmetric? Means if A comma B belongs to R, we have to prove B comma A also belongs to R. So if A comma B belongs to R, that means mod of A minus B is less than or equal to 1. This is happening. That is why A comma B belongs to R. Will B comma A belongs to R? Means from here we have to prove mod of B minus A is less than or equal to 1. If we are able to prove it, then B comma A also belongs to R. This is very simple because if we are taking a minus sign common, then already I have B minus A. And this minus sign can be removed because there is mod. So implies B comma A belongs to R. So therefore it is symmetric. Okay. Next is, will it be transitive? Again the same thing. What should we prove? We have to prove that if A comma B belongs to R, A comma B belongs to R and B comma C belongs to R, then we have to prove that A comma C also belongs to R. Okay. So given that these two belongs to R, means it is given that mod of A minus B is less than or equal to 1 and mod of B minus C is less than or equal to 1. Can I say from here that mod of A minus C is less than or equal to 1? Okay. Certainly, just by seeing only, I can say that this is not right. Means it will not happen. The reason being, I will give you an example. Mod of 3 minus 2 is less than or equal to 1. Mod of 2 minus 1 is also less than or equal to 1. So if we have to prove, then if these two are true, which are true, right? These two are true. Then from here, I have to say that mod of 3 minus 1 is less than or equal to 1. And which is not true. So therefore, there will be some cases where mod of A minus B is less than or equal to 1 and mod of B minus C is less than or equal to 1. And mod of A minus C is also less than or equal to 1. But we cannot generalize it. Okay. So therefore, this will not be transitive. So therefore, reflexive symmetric but not transitive will be option D. Okay. So this is how we have done some CET questions.